Hello students, welcome to the lecture of structure of atom. Till now we have studied about the postulates of Bohr's model and we had derived the formulas of radius, velocity, orbital frequency, time period and energy calculations from the Bohr's model. Now, Bohr's model was not perfect for the determination of a structure of atom, because first of all, Bohr's model was applicable only for hydrogen and hydrogen-like systems. So, there were some drawbacks due to which Bohr's model was not possible to be extended towards heavier atoms. So, before studying the limitations of Bohr's model, we need to know about two very important discoveries which led to the failure of Bohr's model. The failure of Bohr's model was mostly due to these two discoveries. The one was De-Broglie's duality of matter and the second one was Heisenberg's uncertainty principle. So, in the previous lectures we have seen that electromagnetic radiation or light has two types of properties. One is the wave nature and another is the particle nature. So, now the question was, if light can have two properties, wave nature and particle nature, then why cannot matter have two properties as well? If light can act as particle, so why not matter can also act like wave? Due to this theory, due to this assumptions, there was a theory called De-Broglie's dual nature of matter. So, we will now study about De-Broglie's hypothesis. So, in 1924, French physicist De-Broglie proposed duality of matter. He proposed that like radiation, matter should also exhibit dual behavior. That is, both wave-like and particle-like properties. Till now, we had read that electromagnetic radiation has two kinds of properties. One is like wave and one is like particle. We called this as wave particle duality of light. Now we will study about duality of matter. So, let's consider electrons as an example of matter. So, if photons can have both wavelength and momentum, Then electrons can also have momentum as well as wavelength. We know that wavelength is a property of waves and momentum is a property of matter. Momentum is a property of particles. So, De-Broglie said that electrons or similar matter will also have two types of properties. One is particle-like and another is wave-like. So, De-Broglie proposed this equation for relating wavelength and momentum, where wavelength lambda is equal to h by mv, or we can write lambda is equal to h by p, where lambda is the wavelength, h is Planck's constant, with a value of 6.626 into 10 to the power minus 34 joule second. M is the mass of the particle or the mass of the moving particle, and v is the velocity of the particle, and p is the linear momentum of the particle. So, De-Broglie's hypothesis is represented by these two equations, lambda equal to h by p or p equal to h by lambda. Now, this lambda is known as De-Broglie wavelength. This is the wavelength of a moving particle. Now, from these two relations, we can deduce some other relations also. So, next we will see the relation between De-Broglie wavelength, that is lambda, and kinetic energy. So, let's consider kinetic energy as EK. What do we know that the expression of kinetic energy is? Kinetic energy is equal to half of mv square, where m is the mass of the particle and v is the velocity of the particle. We know that if in an equation we multiply and divide with the same quantity at once, then the value of the expression does not change. So, multiplying and dividing by m, what do we get? Ek is equal to half mv squared into m by m. This we can write as half m square v squared by m. Now linear momentum P is equal to product of mass and velocity, that is mv. So P squared will be mv whole squared, that is m squared v squared, right? So we can write kinetic energy as P squared by 2m, right? We can write kinetic energy as P squared by 2m. Therefore, P squared will be equal to 2m Ek. By De-Broglie's hypothesis, lambda is equal to h by p, right? So, if this is P square, what is P? P is square root of 2m Ek. Therefore, lambda will be equal to h by root over 2m Ek. This is the relation between De-Broglie wavelength and kinetic energy. Now, how can we prove the unit of wavelength from this? What is the SI unit of wavelength? SI unit of wavelength is meter. Unit of Planck's constant is joule second. Mass is in kg and kinetic energy is in joule. So, we will derive the unit of wavelength from this expression. So, h by root over 2m Ek. So, joule second by, there is square root 2, we can eliminate 2 from here. So, square root of mass will be kg to the power half and square root of kinetic energy will be joule to the power half. So, if we cancel out, then we get joule to the power half into second by kg to the power half. Now, we know that energy is equal to force into displacement and force is equal to mass into acceleration. Therefore, joule is equal to kg meter square second to the power minus 2. It is joule to the power minus half, right? Sorry, joule to the power half, right? So, it will be kg to the power half meter into second inverse divided by kg to the power half, and there is 1 second. So, second and second inverse will also cancel out. So, we get the unit of lambda as meter. So, we have found out the unit of wavelength. Now, the relation between wavelength and potential difference V. What will be the relation between De-Broglie wavelength and potential difference V? So, if suppose these are two plates with opposite charges, right, and let's consider the potential difference between them is V. Now, if there is a positive charge, then this will move towards the negatively charged plate, and if we have a negative charge, then it will move towards the positively charged plate. So, it will give rise to electrostatic potential energy. Electrostatic potential energy is given by the product of potential difference into charge, that is the magnitude of charge. We do not consider the sign here. Now we know that by the law of conservation of energy, energy will remain constant. So, if we consider kinetic energy in place of electrostatic potential energy, then in this case V into Q will be equal to half mv square. This is considering kinetic energy. Right? So, this is kinetic energy. Now we know lambda is equal to h by root over 2m Ek. And what is Ek? This is V into Q. So, we can write lambda is equal to h by root over 2m VQ. This is the relation between wavelength and potential difference. Now, from this relation of De Broglie's wavelength, we can calculate the wavelength of different types of particles. Let's consider particles like electrons, protons and alpha particles. Okay. So, now we will calculate the wavelength of electron, that is lambda E. So, lambda E will be equal to h by root over 2 me v QE. Now, we know the value of everything except potential difference, which can change. So, lambda E is equal to 6.626 into 10 to the power minus 34 joule second by root over 2 into 9.1 into 10 to the power minus 31 kg, which is the mass of electron, into 1.6 into 10 to the power minus 19 coulomb, which is the charge of electron, into V. So, by calculating, we get lambda E is equal to 12.27 into 10 to the power minus 10 by root over V meters. Now, we know that 10 to the power minus 10 meter is equal to 1 angstrom. Therefore, we can write lambda E is equal to 12.27 by root V angstrom. Next, we will derive the wavelengths of protons and alpha particles. Thank you.